Okay, so here we go with the starter activities to go with chapter 7.2. Feedback on these is really useful because it tells me which things to carry on doing these on. So, usual routine, I'll write out the question, you pause it, try it, the answer will follow. And then when you do the feedback on this, go into Frog. All you have to do is click the submit work, and then a box is there for you to write a comment. And if you could put a comment in there and just tell me, yes, I'm okay on non-uniform rods, centre of mass kind of questions, or whatever, so I know that is something I don't need to keep doing frequently in this sort of section of the work. Okay, so here we go. So we've got a non-uniform rod of mass 50 kilograms. So we've got a weight acting downwards on the rod of 50 G. We've got a normal reaction R at one of the pivots and another normal reaction 4R at the other pivot. The length of the rod is as shown, so 2 meters. Whoops, undo that one. That length there between the pivots is 7 meters, and we've got another 3 meters at the end. And we're going to call this point, one end of the rod is A, the other end of the rod is B, and the distance to the centre of mass from A, X. And we're asked to find the distance from A to centre of mass, which is why I've already, because I knew what I was going to ask, labelled that length as X, as we always take moments about the point we want the distance of the centre of mass from. Okay, so the question is find that value X. So, standard routine, we resolve vertically. R plus 4R minus 50G is equal to 0 since it's in equilibrium. Sorry, you should have paused before we did that. Okay, take moments about A, the point we want us to know the centre of mass from, the distance of the centre of mass from, and in the anti-clockwise direction, we're going to have R and 4R are acting anti-clockwise, so we get 2R plus, and just be careful here, it's the total distance, so it's 2 plus 7 is 9 lots of 4R is equal to, in the anti-clockwise direction, we've then got the weight. And the distance to the weight is X, so we get X 50G in the anti-clockwise direction. So now we've got 2R, 36R is 38R equals 50GX. We can then substitute in for the R, because we know from here we've got 5R equals 50G, so R equals 5G, and then we can take that and we can substitute in for R. So if we substitute in for R, we get 38 times 5G equals 50G x, divide down by the 50g, and we get 38 times 5g. Just looking at that, 38 times 5g, 38 times 5g over 50g equals x. So the g's cancel, the 5's cancel, so x equals well, looks like I've made a mistake. Yeah, R isn't 5g, is it? That's a bit stupid. So hang on, let's just tidy that up. So that's not 5g, but that is 10g. That is 10g. So now we've got 10g there, that's better. That looks more like it. So the g's cancel, so we end up with 38, the zeros cancel. So we end up with 38 over 5, which is equal to 7.6 meters. Sorry about that, there's a silly error in there with the number work earlier on. Okay, so you should have ended up with x equals 7.6 meters. Okay, let's go again then. So second starter question. We've seen this style of question before, so we're going to take the cliff kind of thing, and this will be particle A. It's dropped, so dropped means that the speed is going to be u equal 0, and particle B is thrown up from the base, which will take as our origin, and UB then is going to be equal to 40 meters per second. They're travelling in the same straight line, and they start off 200 meters apart, and I want find the relative velocity when they collide. So first of all, so you can try that. So pause, and then when you've had a go, start it again. So it's the usual routine at the start. We need to find the time at which they collide. So first find time, collide. So we know it's going to be constant acceleration because it's in a projectile kind of context. No other forces are acting other than gravity, and we're going to take positive as up, so our acceleration is down. So let's first of all consider A. Constant acceleration upwards on A, and we get U equals 0. A equals negative G because it's acting downwards. Position of A is what we're trying to find, so S is equal to SA, and we're looking for the time, call it capital T. So what do we now have? S equals ut plus a half at squared. Yeah, we need our state phase. Yeah. And because we want the position rather than just how far it's moved, plus S0. Yeah, want position, not just displacement. Yeah, we want its position relative to the origin, which is basically where it starts, which is this bit, yeah, where it starts, its starting position, and then how far it's moved is this bit here. Okay, so we get its current position of A is equal to 0t plus a half negative g t squared plus its starting position, which was 200 relative to our origin down here. So SA equals minus a half gt squared plus 200. Okay, now we're going to look at constant acceleration, positive still upwards, on B. U is equal to 4t. A is minus g again, T is capital T, and S is the position of B. So again, we're using S equals ut plus a half at squared plus S0. We can substitute in, so SB is equal to 40 lots of T minus a half g T squared, and S0 for B is 0 because it starts at the origin. So they collide. So when collide, SA must be equal to SB. The position of the two is the same. So we get minus a half GT squared plus 200 equals 40t minus a half gt squared. Add the half gt squared to both sides, so those cancel. So t equals 200 divided by 40, which is 5 seconds. So that's the time at which they collide, but we want to know their relative velocity when they collide. So in effect, that's how hard or fast they are travelling relative to each other when they hit each other. So we need to find the speed of A, or the velocity of A. So constant acceleration again, constant acceleration on A. Again, we've got to keep the same positive as up. So V, when they collide, V of A, or V is equal to VA. U is 0 for A, wasn't it? It was dropped. A equals minus G and T equals 5. So V equals U plus AT. So VA equals 0 minus 5G. Constant acceleration on B, positive up. So V, the final velocity when they collide, is VB. U this time is 40. A is equal to minus G, and T again equals to 5 because that's the time at which they collide. So again, using V equals U plus AT, we get VB equals 40 minus 5G. So the relative velocity is one take away the other. So the velocity of A relative to B is equal to VA minus VB, and that's a little bit you've not seen before. So we've got minus 5G minus 40 minus 5G. So that gives minus 40 meters per second is this relative velocity when they collide. In other words, their relative speed will be 40. Okay, last little reminder kind of question. And this is the one that we've been building up on. So I'm going to add an extra little bit to this question. So it's this projectile one. This time we're going to project it at a speed of 40 meters per second, at an angle of 30 degrees to the horizontal. And we want to find the time after projection when the particle is travelling perpendicular to the initial direction of motion. So, have a go, pause this, have a go, and then start it again, obviously, and see the answer to compare. So we know that it's a projectile motion, and we want the angle to now be perpendicular to the original direction. So originally we had, let's just make that a little bit larger so we can add on to the diagram. So originally we had 40 at 30 degrees. So now if we're perpendicular, we've got a new speed, V, at 60 degrees. Okay, so the key factor to remember here is that the horizontal speed remains unchanged. Horizontal velocity is constant. So we're going to consider horizontal speed. Okay, so to do that, we have to break these down into their components. So horizontally here, we've got 40